I am Adam Schneider. I'm an astronomer at the University of Toledo, and I am fascinated. I'm absolutely fascinated by the idea of alien worlds, of planets that exist around stars other than our own. These are also known as extrasolar planets or exoplanets. And just thinking about these objects, just pondering their existence, leads to some really, really big questions, some really intriguing questions, and in my opinion, very important questions, such as, do extrasolar planets exist? It wasn't that long ago that we didn't know the answer to this question. Spoiler alert, we know it now. And the rest of the talk wouldn't be quite as interesting if the answer was no. But we'll get to that in a minute. Another question is, do they look like those in our own solar system? How are the planets arranged around these other stars? Are systems like our own, are these common out there? Another question, are exoplanets common? If you go out after all these wonderful talks tonight and go out and look up at the night sky, you see a bunch of stars. I know it's Toledo in the winter and you'll probably see clouds, but imagine there's a bunch of stars there. How many of those stars have planets around them? 1 out of every 10, 1 out of every 100 or so, all of them, none of them? That's something I really, really want to know. How do they form? What are the processes that take place to get planets to form around other stars? And can and do they harbor life? Is there life out there? Okay, so not only am I interested in exoplanets, the main interest I have is directly imaging them. I want to actually take pictures of planets around other stars. I want to see them with my own eyes. And this is something that turns out to be a very challenging thing to do. So I want to start here with a picture of a planet, a directly imaged planet, if you will. And it's this one right here. You might have to squint in the back if you can't see it, but trust me, there's a little dot right there. And this isn't just any planet. This is our planet. This is Earth. This is a picture of Earth taken from the Voyager 1 spacecraft at a distance of about 4 billion miles. So let's imagine just for a second that you don't live on this planet. Let's say you live on a planet around our nearest star, Proxima Centauri. Now, if you live on this star and you look towards the sun and you say, I wonder if that star has any planets, and you want to find this dot, you're actually 7,000 times further away than the Voyager 1 spacecraft was when it took this picture. That kind of brings home some perspective about how hard it is to actually take a picture of this guy, right? So imagine how faint it is at that distance. And that's our closest star. Not only that, there's a huge star next to it called the sun that has this huge glare, and so trying to block out the glare from that sun to find this planet would be a really, really hard thing to do. And to be honest, we're not actually imaging other Earths yet. But we are imaging some planets, and we'll get to that in a little bit. But before we get to do the direct imaging part of this talk, we need to know the story of exoplanets. And the story of exoplanets starts with the very first discovered exoplanet, and that's 51 Pegasus b. And so in order to kind of get some perspective on what 51 Peg b is like, it's useful to remind ourselves of what our own solar system looks like. And so this is a schematic of our own solar system. We have 8 planets. Sorry, Pluto. We have 8 planets in our solar system. We have the 4 outer gas giants, and then we have the 4 inner rocky planets. The gas giants are Jupiter, Saturn, Uranus, and Neptune. And then the inner planets are Mercury, Venus, Earth, and Mars. To compare our solar system to the first exoplanet discovered, 51 Peg b, we have to zoom in quite a bit. So this is the sun. The sun's not that big, but this is the sun in the middle, Mercury, Venus, and Earth. And there's Toledo. Maybe in the front you can see it. It's right there. So the orbit of 51 Peg b compared to the orbits of planets in our own solar system is actually right there. So already this is really strange, right? We don't have any planets this far in. Mercury is our closest planet to the sun, and it's way inside of Mercury. Not only that, but to get the size right to compare to our own planets, this one's huge, right? It's bigger than Saturn, and it orbits every 4 days. They don't celebrate birthdays on 51 Peg b like we do here, right? Every 4 days. Happy birthday. So this is a really crazy thing. And so for a second, put yourself in the shoes of the astronomers that found this object, right? Not only are you have to tell people you found this, right? So you found a planet. You're going to announce that you found the first exoplanet. But it looks nothing like anyone ever even predicted would exist. No one in their right mind thought something like this would happen. We're looking for planets that look like the ones we know, right? So, and at the beginning, in fact, a lot of astronomers thought this would be disproven very soon. They kind of brushed it off, no big deal. But it turns out it's real. And so real, in fact, that astronomers, just a few days later, a different group of astronomers confirmed this object. And so this is the very first exoplanet. And so just this one discovery, it cannot be overstated how important this was. Right? We've already answered two of these questions. Do extrasolar planets exist? Yes, they do. Do they look like things that we know of? No, absolutely not, at least in this circumstance. Now, no one's ever actually seen 51 Peg B. It was actually found with a detection technique called the radial velocity, or the Doppler method. So this is an indirect technique where we don't actually get an image of the star, or of the planet, but we see its effect on the star around which it orbits. So how this works, so let's imagine we have a planet orbiting a star. As that planet orbits, that planet actually has a gravitational pull of its own and will actually cause that star to wobble around. And if we look at the light coming from that star, we can see that wobble. And that's exactly how 51 Peg B was found. And for the first 15 years or so of exoplanet detection, this was the dominant detection technique. And this is still used very much today. We're still finding a lot of planets with this method, and it's working out really well. But there's a second exoplanet detection method, an indirect method where we don't actually see them, called the transit method, which is also hugely, hugely successful. So the way this one works, so let's say you're looking at a planetary system and it's perfectly aligned, so it's edge on. If there's a planet that starts crossing in front of that star, and you're monitoring how bright that star is, the brightness of that star will actually dip down a little bit while that planet comes in front of it. And when that planet goes all the way to the other side, the brightness will come back up. And so the idea is, if you look at stars, you monitor how bright they are. If you see these little dips, you have found an exoplanet. And if you've ever heard of the Kepler telescope, that's exactly how the Kepler telescope works. This has been immensely successful. So successful, in fact, so if we look at how many planets we found as a function of year. So 1995, that's the first one. Here we have the number of new planets. The blue plots are the ones that were found with the radial velocity technique, the one that found 51 Peg B. And all these red ones are the ones that found with the transit technique. But it stops at 2014, but you get the idea. This isn't done yet. So these are all the planets found with Kepler so far, and you can see it gets bigger and bigger. Right? So how crazy is this compared to what we've known so far? This has basically revolutionized our understanding of exoplanets. We now know of hundreds of them out there. We're getting into the thousands of exoplanets. Right? Thousands of planets. That's so many. And so what do these things look like? What kind of planetary systems are we finding? Right? We looked at what 51 Peg B looked like. What do these other ones look like? Well, a lot to look at, but here's an idea. So we actually have the inner planets of our own solar system up here on the left. This is Mercury, Venus, Earth, and Mars. And these are all the other ones, and the sizes are kind of appropriate. And we can watch these all wiggle around, and it looks very cool. So these aren't all of the systems. These are all the ones that actually have more than one planet. You can see they come in all different types of architectures. There are ones that, maybe look a little bit like ours, but they have big planets. There are huge planets out there. There are little ones going really fast. There's a lot of stuff going on. But with Kepler, we have answered a very, very important question. Thank you. Are they common? They are. We actually know now, statistically speaking, that every single star has at least a planet. Every single one. So go out and look at the stars at night. They all have them. How awesome is that? Right, so this is good if you're an exoplanet astronomer because, helps with job security. But there are so as successful and as revolutionary as these techniques have been to find exoplanets, there are some limitations, right? So if we go back to this real quick, you'll see that, these are our inner planets and these are all the planets that Kepler found. Jupiter is kind of way out here on this plot. And this isn't finding many Jupiters, right? So the whole picture of what's going on with these exoplanets is incomplete, right? The reason that you can't find things like Jupiter with these methods, for the most part, you can a little bit, is that you have to monitor the entire orbit. So Earth goes around the sun in about a year. And so you have to look at a star for a year to see that planet. If you want to find something like Jupiter goes around every 5 years. And so you would have to monitor one single star for 5 years. That's really hard to do. That's a lot of resources. And so for the most part, we're finding things that go around much shorter than that. The second thing, and the reason that Kepler was very successful, is it looked at a bunch of very, very faint stars. The idea was to stare at a bunch of faint stars for a long time and find all these little dips, which is really great for the statistics. But if you want to follow up these objects, if you want to try and do some detailed studies of, say, the atmospheres of these exoplanets, since they're faint, they're actually really, really far away. It makes it really, really hard to study them any more than you've already just detected the planet. And so that's where direct imaging comes in. Direct imaging is a complementary approach to try and really fill out the picture of what's going on with exoplanets. Okay, and that's where GPIE comes in. So I'm part of the Gemini Planet Imager team. It's also called GPIE, sorry. And there are a lot of reasons GPIE works, but there's 4 big reasons that GPIE can do what it does. First, it has to be on a very large telescope. So this on the Gemini South telescope, which is down in the mountains of Chile. And it's on this 8-meter telescope, so it's 8 meters, it's really big. And this is actually GPIE right down here at the bottom. It's really hard to see, but it's this camera that goes on the bottom. GPIE also has something called a coronagraph, and a coronagraph is simply, so let's imagine you're looking at a star is really bright. You basically want to put a disk in front of it so you can block all the starlight coming from that star, so you can look for things around it. So it has a coronagraph. And it also has something called adaptive optics. So we live on Earth, and Earth has this really great atmosphere that allows us to breathe, and it's wonderful. But for an astronomer, we hate the atmosphere. Light comes, imagine light coming from a star. It comes to your telescope on the surface of Earth, and it kind of bounces around through all the air particles and gets scattered, and it really unfocuses your star. And so what adaptive optics does is it focuses all that light back into one single point to really lock down where the star is and the planets around it. And the last thing is an optimized target list. So we don't go out there and just point our telescope at every star we see. We have to point at the right stars. And it turns out the best stars are young, nearby stars. Nearby because nearby things are brighter. And young because young stars have young planets. And young planets will actually glow with some leftover heat from their formation. And that makes them brighter for our telescopes. And so let's show off some of GPIE's results. So this is really cool. So this is Beta Pictoris b. This is actually a known exoplanet, a directly imaged exoplanet that was known before Gemini Planet Imager. This is an image on the left side from a previous generation instrument, and this is the planet right there. Not too spectacular, it's just a little dot, but that's a planet. So this is a really, really hard thing to do, so appreciate it. This is an image from GPIE. It's actually kind of a raw image, very little processing going on. These little spots are not planets, those are there for calibration purposes, but there's the planet right there. And you'll see this big disk in the center and this one over here, that's the coronagraph that I mentioned earlier. But the amazing thing is that this image over on the left side took an hour. This one on the right side took 60 seconds. So GPIE is really, really advancing our methodology for detecting these planets. But this is a known planet, this isn't something new. Oh, this is the final added together image. So look at all this signal. This is just wonderful, right? That's a beautiful exoplanet around another star. It's about 5 times the mass of Jupiter, this object is. So this is one we know of. Let's look at something new. This is our first discovered exoplanet from GPIE. This is the first new discovery. And this is called 51 Arri b. So 51 Arri is a star right under here, right under the circle. And this is about where Saturn's orbit is. And B is the planet. And this is actually the lowest mass directly imaged planet we've gotten so far. It's about 2 times the size of Jupiter, which I know is big for our solar system, but we're getting down there. We're starting to make progress into getting to lower mass planets. And the amazing thing about GPIE, something that we didn't really talk about earlier, is the instrument, the science data that you get. So you don't just get one image, you actually get what's called a data cube. All right, and so this is another image, basically the same thing. So 51, the star is in the center, and the planet's there, but you don't really see it yet. So if you watch this one on the left, you'll see kind of the planet appear and then go away. And so what this is actually doing is scrolling through different wavelengths. And if you just plot the brightness of that planet as a function of this wavelength, you see this really nice curve. Now, the way direct imaging used to work is if you go and take a picture of a star and you see a little spot next to it, that could be a planet, but it could also be a background star, it could be a background galaxy, it could be a foreground star, it could be anything. You don't really know. So what you do is you take a picture, you see something, and then you wait a few years, go back to that same star, take another picture, and say, is it still there? Then maybe it's a planet, right? Maybe you'll see a little orbital motion, but it should still be there at that next time. With GPIE, we don't have to do that anymore. We know that this is exactly what a young planet should look like in a spectrum. Not only that, we don't have to wait these extra years. We can actually find something out about the atmospheres of these objects, just from this little piece of data here. So we actually know with this planet that it has methane in its atmosphere, right? So we're actually finding out things about the atmospheres of these extrasolar planets. And knowing that there's methane tells us something about its temperature, and so this is a really, really nice thing for us to do. So one of our initial questions was, how do planets form? Since GPIE is actually looking at young planets, young exoplanets, we are looking at basically different snapshots in the ages of planets, how they form. Right? So we're getting little pictures of what a planet looks like at 20 million years old, 100 million years old, et cetera. And so we're really starting to fill out this picture. So I would say that's in progress. Okay, so back to the theme is interaction. So I want to depart from direct imaging for just a second and talk about where science is going, and not just astronomy, but a lot of different science. We're entering the era of what's called big data. And so big data is exactly what it sounds like. It's just a lot of data. And in many cases, it's too much data for one person or a group of people to efficiently look at on their own. And so in some of these cases, scientists are asking for help from you, from anybody that wants to help. And this is something called citizen science. And this all started, for me anyway, with something called the Galaxy Zoo. So the Galaxy Zoo is here. It's part of the Zooniverse. And so you can actually go and help scientists. Yeah, the Zooniverse. You can actually go and help scientists classify different types of galaxies. You can go sit and literally do science on your own, looking at really beautiful pictures of galaxies all day long. I've done this. I've wasted some time on this. So you can actually, how many spiral arms are there in these galaxies? Do they have a central bulge? All these cool things. But this was this was the first one as part of the Zooniverse. But since then, it's been so successful that it's expanded to quite a few other scientific projects, dozens of scientific projects. And to relate that back to what we've done before, there's one called Disk Detective, where you can look for disks around other stars that these are the precursors to planetary formation. There's also one called Planet Hunters, where you yourself can go look at that Kepler data, the Kepler data I talked about that found all those exoplanets. You can go look at that data and look for transits on your own. You could discover an exoplanet. So this is really, really exciting stuff. If you're not into astronomy, there's also things called like the Plankton Portal, my personal favorite. And I think it's because they look like little aliens. You can go classify different kinds of plankton. And so I encourage each and every one of you to become a citizen scientist yourself. It has never been more easy or more fun to get involved with these big science missions. Thank you.